Atoms are the tiny building blocks of everything we see, touch, and breathe. They form the tapestry of the universe, from simple elements to complex organisms. Understanding atoms reveals the essence of existence. Each atom has a nucleus and electrons forming all matter. Scientists unveil atomic mysteries impacting science and technology. Atoms are central to every process in the universe. Their interactions shape our world. Atomic principles drive technological advancements. Exploring atoms unlocks potential innovations. Appreciate the pivotal role of atoms in the universe and life. At the heart of every atom lies its nucleus, a dense core composed of protons and neutrons. Protons, carrying a positive charge, and neutrons, which are neutral, form the nucleus's bulk. The number of protons, known as the atomic number, is crucial as it defines the element's identity. Surrounding the nucleus is a cloud of electrons, negatively charged particles that move in probabilistic orbits. These electrons are not fixed in position, but occupy regions of space called orbitals. The arrangement of electrons in these orbitals determines the atom's chemical properties and its ability to bond with other atoms. Electrons exist in quantized energy levels, or shells, and they can jump between these levels by absorbing or emitting energy. This behavior is fundamental in explaining atomic emission and absorption spectra, which are unique to each element. The atomic model has evolved significantly over time, from the early plum pudding model to the more sophisticated quantum mechanical model we use today. The modern view of the atom encompasses not only the idea of particles, but also the wave-like properties of electrons. Atoms rarely exist in isolation. They are naturally inclined to bond with other atoms to form molecules. Covalent bonds occur when atoms share electrons, allowing them to achieve a stable electron configuration. This type of bonding is prevalent in organic molecules, where carbon atoms form strong covalent bonds with hydrogen, oxygen, and other elements. Ionic bonds result from the transfer of electrons between atoms, leading to the formation of charged ions. These oppositely charged ions attract each other, creating ionic compounds like sodium chloride or table salt. Metallic bonds are characterized by a lattice of metal cations surrounded by a sea of delocalized electrons. This electron cloud permits the free movement of electrons throughout the metal, accounting for properties such as electrical conductivity and malleability. Metals like copper and aluminum exhibit these characteristics, making them invaluable in electrical and structural applications. The diversity of atomic bonds underscores the versatility and adaptability of atoms in forming a myriad of compounds and materials. Understanding atomic bonds thus opens the door to innovations in fields ranging from nanotechnology to pharmaceuticals. Within the atomic nucleus, subatomic particles, protons and neutrons play crucial roles in defining an atom's characteristics. Protons determine the element's identity and contribute to the nucleus's positive charge. Neutrons add mass and stability to the nucleus, affecting the atom's isotopic nature and nuclear reactions. Electrons, the third type of subatomic particle, are fundamental to chemical bonding and atomic interactions. These negatively charged particles are much smaller than protons and neutrons, but are vital in defining an atom's chemical properties. The interactions and arrangements of these subatomic particles are dynamic, influenced by forces such as the electromagnetic force and the strong nuclear force. Section 5. Quantum mechanics, a new perspective on atoms. Quantum mechanics revolutionized our understanding of atoms, describing subatomic particles' behavior. Particles like electrons exist in probabilistic states described by wave functions. The Heisenberg uncertainty principle states that an electron's exact position and momentum cannot be simultaneously known. Energy levels within an atom are discrete, and transitions involve quantized energy. This explains the unique atomic spectra of elements. Quantum entanglement connects particles, influencing each other's states instantly. This challenges classical notions and impacts quantum computing and cryptography. Section 6. Atomic energy and chemical reactions. Atoms are not only the building blocks of matter, but also the carriers of energy, playing a pivotal role in various chemical and nuclear reactions. One of the most familiar chemical reactions involving atoms is combustion, where substances react with oxygen to release energy in the form of heat and light. In the realm of nuclear reactions, the energy released is orders of magnitude greater than in chemical reactions. Nuclear fission, where a heavy nucleus splits into smaller nuclei, releases vast amounts of energy and is harnessed in nuclear power plants to generate electricity. Nuclear fusion, the process that powers the sun, involves the combination of light nuclei to form heavier ones, releasing energy in the process. Photosynthesis is another crucial atomic process, where plants convert sunlight into chemical energy stored in glucose molecules. Understanding atomic energy and reactions is essential for addressing global energy challenges and developing sustainable technologies. Section 7. Atoms and the Cosmos. The universal connection. Atoms played a fundamental role in the formation and evolution of the universe, from the initial moments after the Big Bang to the present day. In the early universe, temperatures and densities were extreme, leading to the synthesis of the lightest elements, hydrogen and helium. These primordial atoms formed the building blocks for stars, galaxies, and eventually all matter in the universe. As stars form and evolve, they act as cosmic forges, fusing lighter elements into heavier ones through nuclear fusion. This stellar nucleosynthesis is responsible for creating elements like carbon, oxygen, and iron, which are essential for life as we know it. When massive stars end their life cycles in supernova explosions, they scatter these elements across the cosmos, enriching the interstellar medium. The study of atoms and their cosmic significance highlights our connection to the universe, emphasizing that the same fundamental building blocks are present in both the distant stars and our own bodies. Section 8. Technological advancements through atomic insight. The understanding of atomic behavior has paved the way for numerous technological advancements that have transformed society. One of the most significant applications is in the field of electronics, where semiconductors, composed of elements like silicon, are the foundation of modern computing and communication technologies. In the medical field, atomic insight has led to the development of imaging technologies such as magnetic resonance imaging, MRI, and positron emission tomography, PET. Nuclear power derived from fission reactions has become a significant source of electricity in many parts of the world, offering a low-carbon alternative to fossil fuels. The ongoing research into nuclear fusion aims to harness the same process that powers the sun, promising a nearly limitless and clean source of energy. Electron microscopes, which use beams of electrons instead of light to magnify specimens, allow scientists to observe materials at the atomic level. This ability to visualize and manipulate atoms has opened up new possibilities for designing materials with unprecedented properties and functionalities. Section 9. Historical context and pioneers of atomic theory. The journey to understanding atoms has been marked by the contributions of several key figures who laid the groundwork for modern atomic theory. The concept of atoms dates back to ancient Greece, where philosophers like Democritus proposed that matter was composed of indivisible particles. However, it was not until the 19th century that John Dalton formalized the atomic theory, suggesting that each element consisted of unique atoms with specific weights. The discovery of the electron by J.J. Thomson in 1897 marked a significant milestone in atomic theory, revealing that atoms were not indivisible but contained subatomic particles. Ernest Rutherford's gold foil experiment furthered this understanding by demonstrating the existence of a dense, positively charged nucleus within the atom. Niels Bohr introduced the Bohr model, which depicted electrons orbiting the nucleus in quantized energy levels. The development of quantum mechanics by scientists like Erwin Schrödinger and Werner Heisenberg revolutionized atomic theory, offering a new perspective on the behavior of subatomic particles. Section 10. Conclusion. The importance of understanding atoms. The exploration of the secret life of atoms offers a profound understanding of the universe's fundamental structure and the processes that govern it. Atoms, as the building blocks of matter, play a crucial role in shaping the physical world, from the simplest elements to the most complex biological systems. Their interactions drive chemical reactions, power the stars, and enable the development of technologies that improve our quality of life. Studying atoms is not merely an academic pursuit, but an essential endeavor that impacts various fields, including energy, medicine, and technology. Knowledge of atomic behavior and interactions enables us to harness energy more efficiently, develop new materials, and create innovative solutions to global challenges. It also enhances our appreciation of the interconnectedness of all matter, reminding us of our place in the cosmos. By continuing to explore and understand the secret life of atoms, we unlock the potential for scientific and technological advancements that can transform our world for the better.